So you've probably been just dying to know what atoms can break the octet rule. And again, what that means is that some atoms will have less than an octet and some will have more than an octet. And in Chem 100, the Chem 100 classes, this is something, honestly, we never talked about. These aren't as common as the times when you do have an octet, but they are important. And here in Chem 222 in the Big Kids Club, we need to talk about these so you're prepared to deal with it. So if you're going to have a violation of the octet rule, it's usually with elements right around boron. So that would be like boron, beryllium, aluminum under it. Those are the ones that sometimes go under. And ones that go over, we're going to see, are period 3 and lower. So boron trifluoride, BF3 on the left, that actually only has 3 pairs around it. So it's under the octet. On the other hand, SF4, sulfur tetrafluoride, there's an invisible lone pair right there. So sulfur tetrafluoride actually has 5 pairs around it. And we'll see how to analyze this here in a little bit. Let's look into this in a little bit more detail. Boron trifluoride, central atom. Boron is first, it's going to be boron. Valence electrons, boron group 3, fluorine group 7. So 7 times 3 for fluorine, 21 plus 3 for boron, 24 valence electrons. 24 divided by 2 will be the electron pairs, 12 electron pairs. Boron in the middle, F's around the outside. Put the bonding pairs to connect the outer atoms to the inner atoms. Lone pair electrons on the outside atoms make an octet first. If there's any left over, put them on the inside. So boron trifluoride looks like this, all right? And fluorines are fine, 3 lone pairs and a bonding pair is the octet. But boron is what we're dealing with here. Boron has only 3 pairs. And for a lot of the atoms we've looked at so far, this wouldn't fly. But boron's actually okay with this. Boron can be less than an octet around the central atom. And as I said, it can have an octet, and we'll see examples of this. But boron and aluminum and beryllium, these 3 often will have less than an octet, and it's okay. Now, if this was carbon, nitrogen, or oxygen under an octet, no way. You'd be stealing electrons, making double bonds and stuff like that. So this is a very select set of atoms where this is possible, but it is very common. This is the first time where you can maybe begin to see why I called in Chem 221 group 3A metals the twisted metals, because these guys can have only 3 pairs of 4 around them. That's very unusual, and sometimes they try and bond with each other to make these weird kind of bonds. We'll talk more about this later, but the twisted metals comes from the fact that these atoms are capable of making less, or molecules with less than an octet around them, which is totally cool. Beryllium is too, but that's because it's kind of quasi-covalent. But anyway, I'm babbling. Punchline here. There's not too many that can go under an octet in the central atom, but boron and aluminum, sometimes gallium, beryllium, definitely can do that. Hydrogen also just has 1, but hydrogen doesn't count for much. Let's talk about the ones that can go more than 4. So let's go back to sulfur tetrafluoride. All right, so the central atom, sulfur, because sulfur is listed first once again. Valence electrons are next. So fluorine is 7, 7 times 4, 28, plus sulfur 6, 28, plus 6 would be 34 valence electrons. You divide that by 2, that would be 17 pairs of electrons. So sulfur in the middle, the fluorines around the outside. Connect the outer fluorines to the middle sulfur with a bonding pair. Lone pairs around the outside atoms first to give them an octet. If there's any left over, put them on the inside. And that's where things get interesting. So the fluorines in this structure, they have 3 lone pairs and a bonding pair. They've got their octets and they are happy. But there's 1 more pair left over, and that extra pair is going to go on the central atom. You don't want to put it on fluorines. Actually, you'll never put it on the outside atoms. Outside atoms will always obey the octet rule unless they're hydrogen. But you can sometimes put extra electrons on the central atom. Elements outside the second period can do this. So that means elements in the third period and lower can make more than 4 bonds around them, like sulfur's doing right here. Now, sulfur is totally happy making only 4 pairs, having an octet. But if the electrons are there, sulfur and things outside the second period can make more than 4 bonds. A corollary of what that statement is, too, is that elements in the second period and first period will never have more than 4 pairs, all right? So fluorine will never have more than 4 pairs. Carbon will never have more than 4 pairs. That's something to think about while we go through these molecules. All of the examples we've seen so far have had an even number of valence electrons. So when you divide by 2, you get another whole number, okay? But you can have odd number of valence electrons. And what this means is you have what's called a paramagnetic compound. And in Chem 221, towards the end, we saw how paramagnetic atoms were atoms where there was an up electron without a down electron, and they were more reactive, etc., etc. A paramagnetic compound is the same idea. You've got an odd electron running around, and these molecules are usually super reactive. Sometimes they're called free radicals. A free radical is just a paramagnetic compound or a paramagnetic atom. So let's look at an example of how you would do this kind of molecule. So let's do the Lewis structure for nitrogen dioxide. Well, central atom, first atom listed, nitrogen, no problem. Valence electrons. Oxygen is 6 times 2 is 12. Nitrogen is 5. 12 plus 5, 17 valence electrons. And if you divide that by 2, you get quote-unquote 8.5. Or, as I prefer to think about it, you have 8 pairs plus 1 odd electron. Think about that. Now, when you put these molecules in a Lewis structure, start with nitrogen in the middle, connect the outer atoms to the inner atoms with bonding electrons, put lone pair electrons on the outer atoms first, and if there's anything left over, put it on the inside. And that's where it gets kind of interesting. Now, that odd electron is going to occupy its own space, all right? So initially, you have an oxygen, a nitrogen, and an oxygen. 1, 2, 3, 4, 5, 6 lone pairs, 7, 8 with the bonding pairs. So that extra electron ends up by itself on the nitrogen, and that's its own like space in that thing. Now, because nitrogen has only 2 bonding pairs and the odd electron, it needs to have a semblance of an octet. So it will make a double bond, and this double bond could come from the left oxygen or the right oxygen. So this structure isn't just paramagnetic, it's resonating as well. But anyway, you get the idea. Nitrogen's going to be there by itself, or with a lone electron on it by itself. The oxygens then will have everything filled in. So you can totally do paramagnetic compounds, just follow the same rules. Usually the odd electron will go on the central atom because that's like the last thing to get it, all right? Oxygen will take the majority electrons for itself. Formal charges, or formal atom charges, are ways sometimes to predict what the best Lewis structure is going to be. And that's kind of a cool thing to do. Now, formal charges is a little bit weird, but the good news is that this will be about as bad as any of the math we're going to see in the first couple chapters, so it's not too bad. I'm going to start off here with the definition of formal charge. Formal charge equals the group number minus 1/2 the number of bonding electrons minus number of lone pair electrons. That's a lot to say. The predominant resonance structure of a molecule is going to be with the most charges as close to 0. All right? So we're going to use this weird blue structure right here, this blue equation, to figure this out. I don't really like this definition very much. So let's rewrite the formal charge a little bit. Let's say formal charge equals group number, which is the GN part, minus bonds. Now remember, it was 2 electrons per bond. So instead of saying 1/2 number of bonding electrons, let's just subtract the number of bonds. Same thing. and then minus lone pair electrons. All right, so formal charge equals group number minus bonds minus lone pair electrons. If your head is still twirling like that poor little girl in the Exorcist movie, I understand. I will make clear of this here in a little bit with some examples, but right now just realize the equation for formal charge, group number minus bonds minus lone pair electrons. You're going to do a formal charge analysis for every atom in a molecule. And when you add all the formal charges together, the sum of those formal charges has to equal the charge on the molecule, if any. So for example, earlier we saw sulfite was SO3 minus 2. All the formal charges on sulfite have to equal -2 because that's the charge on the molecule. On the other hand, we looked at ammonia, NH3 earlier, which had no charge. The sum of all those formal charges will just equal 0. So whatever the charge on the molecule is, that's going to equal the sum of all the formal charges. Let's look at some examples to make this a little bit more clear. Oh, this is a guide for formal charges. It's available in the companion and online. It will have some more information and some more examples, and I do encourage you to check it out.
Formal charge calculations can often help us identify the most stable isomers of molecules. Consider the isomeric compounds, hydrogen cyanide and hydrogen isocyanide. Both structures have octets of electrons about carbon and nitrogen. The formal charge on carbon in hydrogen cyanide is 0. Similarly, the formal charge on nitrogen is 0. In hydrogen isocyanide, the formal charge on carbon is -1. The formal charge on nitrogen is +1. Because the formal charges are non-zero in hydrogen isocyanide, we can predict that this isomeric form is less stable than hydrogen cyanide, as found to be the case.
If you have the formula HCN, there's actually 2 different combinations of atoms that could make that structure. And on the right-hand side here, you can see both of them right there. The top one there is HCN, hydrogen cyanide. And the bottom one, which is HNC, is hydrogen isocyanide. And the question might become, well, which of these is more stable? Well, what was done in the video is they found the formal charge for the H, C, and N in both cases. And in green, under the 2 structures, you can see what the results were. It's always group number minus bonds minus lone pair electrons. So let's start with hydrogen. Hydrogen has just a single bond in both molecules. Group number of hydrogen is 1. There's 1 bond connected to hydrogen, and hydrogen has no lone pair electrons. So formal charge for hydrogen in both structures, 1 minus 1 minus 0, formal charge equals 0. Formal charge of 0, we're going to see, is good in these kind of molecules. Now, the carbon in hydrogen cyanide, this carbon right here, group number 4 minus number of bonds, and there's a single and a triple, so that's 4 lines, 4 bonds total, so 4 minus 4. Carbon has no lone pairs, so the formal charge of that carbon is also 0. And then nitrogen, right there on the end, nitrogen group 5, 5 minus 3 for the bonds, minus 2 for the lone pair electrons. Notice each lone pair electron counts as 1. Nitrogen there goes to 0. Now, if this is a good resonance structure, the sum of the formal charges, 0 plus 0 plus 0, will equal the charge on the molecule. HCN is neutral, there's no charge, so this is a good resonance structure. Let's look now at the bottom one, hydrogen isocyanide. Now, hydrogen is still 0, but the nitrogen in the middle now is 5 group number minus 4 bonds minus 0 lone pair electrons. That nitrogen is positive 1. And the carbon on the far right, group number 4 minus 3 bonds minus 2 lone pair electrons, that carbon is a -1 formal charge. If you add up the 0, the +1, and the -1, it also goes to 0, so that's a legit resonance structure. But when it comes to the more stable structure, the more zeros you have, the better. And HCN has a lot more formal charges of 0 than hydrogen isocyanide. So we would say here that HCN is more stable. And making hydrogen isocyanide is tough. You have to really cool it down, keep it very cold so it doesn't rearrange and stuff. It can be made, but it's just very difficult. HCN, on the other hand, is relatively stable. It's incredibly poisonous and toxic, but it is stable. So woohoo, go chemistry. So more zeros, more stable. HCN more stable than HNC with the +1 and -1. Carbon dioxide, we drew the structure there earlier. Oxygen group number 6 minus 1/2 bonding electrons, 1/2 of 4, or this is just equal to 2 because there's 2 bonds, either way you want to do it. But the oxygen has 4 lone pair electrons, so the oxygen is going to be 0. And it's not only this oxygen, but it's actually the other oxygen too, because they're both in the same electronic environment, 2 bonds, 2 lone pairs. The carbon, group 4 minus 1/2 of 8, or if you'd rather, and this is what I recommend, just count the number of bonds. There's 4 bonds and no lone pairs. Carbon's formal charge is equal to 0. So the sum of the formal charges, 0 plus 0 plus 0 for all 3 atoms equals 0, and that's good. CO2 is neutral. This is a good structure. CO2 is very stable. It's so stable we're running into problems with greenhouse gases, stuff like that, but that's another story. CO2, very, very stable. However, that's not the only way you could write CO2. I didn't share this with you, but you could have, for example, a triple bond on one side and a single bond on the other. Let's look at the formal charges here. So the oxygen on the right now has 6 lone pair electrons and only 1 bond, or 1/2 of 2 bonding electrons. Formal charge -1. And the left-hand side oxygen has 1/2 of 6, or 3 bonds, and 2 lone pair electrons, +1. So notice that this CO2 has a +1 and a -1. Carbon is still going to be 0. All right, carbon hasn't changed. It still has 4 bonding pairs and a group number of 4, so it's going to go to 0. So if you analyze these formal charges, -1 plus 0 plus 1 equals 0. So this is a good structure. It's definitely a resonance structure. However, it's not as stable as the last one. There's a lot of things in the real world that want to attack positive and negative things. And so if you have a -1 formal charge and a +1 formal charge, that's like a beacon in the night. Negative things will be attracted to positive things, and positive things will be attracted to negative things. So things like water and oxygen or ions will then attack the CO2 and make CO2 turn into something else. If you've taken biology and you've studied carbonic acid, CO2 reacts with water when it has the resonance form shown right here. It doesn't attack a carbon dioxide when you have 2 double bonds because all the formal charges are 0. So this is a way to tell what a better resonance structure is. And definitely having 2 double bonds is better than having a triple bond and a single bond. And we can do that through formal charges. Here's a kind of an overview that some people like. Again, by default, you generally want to have a formal charge equal to 0. And all of these central atoms, if they're in that kind of electronic environment, will have a formal charge of 0. So for example, here's the carbon dioxide with a triple and a single, and here's, as we found, the better carbon dioxide with 2 doubles. But on the carbon, all the formal charges are 0. Notice that all of the carbons in that box right there, all of the carbons except for the one freak of nature, and I don't want to even worry about that one right now. That's for organic chemistry. It's called a carbene, long story short. It's really messy. All the other structures, ignore the one in the middle there, have just bonds around them, no lone pairs. If you put lone pairs around the carbon, or if you start taking away electrons like on the right, your formal charges get really messed up. So generally speaking, carbon's going to want to have 4 bonding pairs around it. And if you look at nitrogen underneath, nitrogen likes to have 3 pairs and a lone pair, and the oxygen under that, 2 pairs, 2 bonding pairs, 2 lone pairs. You can kind of make predictions as to what the more stable version of these things are. And we're going to talk more about this in a little bit. So just remember that formal charges can be used to tell what the most stable version of a structure can be. Let's go back to boron trifluoride. I drew it with 3 single bonds, but why not draw it with a boron fluorine double bond? I mean, that would give boron the octet and stuff like that. Well, this would be a good thing to do on your own here, but your formal charges get really screwy when you make a double bond. Now remember, boron's in group 3, and 3 minus 4 pairs on the structure on the right, no lone pairs, gives it a -1 formal charge. And fluorine group 7 minus 4 lone pairs and 2 bonds, that would give it a +1 formal charge. That would make fluorine have a really weird thing. Fluorine never makes double bonds. All right, maybe if you're in a vacuum in the heart of space in the sun or something, but in normal day-to-day things, fluorine doesn't make double bonds ever, okay? So just keep that in the back of your mind. So even though we could give boron an octet and fluorine has an octet, formal charges absolutely scream at you to not give it that, all right? Fluorine really hates making double bonds. Let's determine the formal charge on the formate ion. And this little thing right here, which is HCO2 -1, is a pretty powerful little ion. And there's 4 different combinations and none of the above. All right, so what you want to do is take the group number, subtract the lone pair electrons, and subtract the number of bonds. So for the oxygen on the left, oxygen's group 6, 6 minus 4 for the lone pair electrons, minus 2, that oxygen, formal charge of 0. Oxygen with 2 bonds and 2 lone pairs always has a formal charge of 0. Carbon, the next arrow over, carbon group 4, 4 minus 4 bonds, no lone pairs, so 4 minus 4. That carbon also goes to 0. And finally, the oxygen on the right, group number 6, minus 6 lone pair electrons on that thing, minus 1 bond, don't forget the bond, that's going to have a formal charge of -1. So if you look at those options right there, the answer here is going to be D. Hydrogen on the top right there, group number 1, minus 1 bond, minus no lone pair electrons, is going to be 0. So notice that in this molecule, 0 for the hydrogen, plus 0 minus 1, all of that gives you the -1 that formate charge has. If you have a negative charge, something has to have a non-zero formal charge. And in this case, it's the oxygen with the single bond and the lone pairs. If this would have been a neutral compound, then we would have hopefully gotten to a structure where everything had a formal charge of 0.